Then let's begin. I hope everyone's doing well. Next week we have our midterm exams. I want to talk a little bit about that. Okay. Okay. So we'll get started at 7. It will run until you'll have 2 hours for the exam. Okay. So it'll be 2 hours. It'll go from 7 to 9. Okay, so yeah, 2 hours for the exam. We'll go from 7 to 9. You'll have it will be all multiple choice. Okay, I will provide scantrons as well as the reference tables. Okay, these reference tables that I've just passed out to you guys, these are for you to keep them safe. You'll need them in future weeks, not next week. Next week I will include the reference tables as part of the exam. But for the other weeks you will need them, and they will come up for quizzes and things like that. So you'll need them for the quiz and to follow along in class. So make sure you keep these. They're also posted online. If you misplace yours, you can print out new copies for yourself. They're posted online as well. So as far as the multiple choice goes, you can expect a mix of conceptual and calculation-based questions. Okay. I think for the calculation-based questions, it will be you should review past quizzes. I'll say past practice quizzes. Okay, I think that will be a good tool to study. And as far as the conceptual question goes, kind of review definitions from the notes or textbook. Are there any questions? Okay, so that will be midterm exam next week. Okay. Then if we're good there, okay. So I'll just say make sure do not forget your calculator. Okay, and then pen or pencil is fine. But I recommend pencil and eraser, okay? Because sometimes you'll make a mistake or something. So just make sure you bring your calculator, pen and pencil, and then bring some kind of photo ID also. So I'm supposed to do checks to make sure you are you. Yes? Oh, yes. You are allowed a note sheet. Okay. A note sheet, letter size. So standard paper, 8.5 by 11. Writing on one side only. Okay. Yes, another question.
Are we allowed to bring our phone in? I mean, not to use it for a calculator, but is there any...
Yeah, I'm not gonna have a metal detector or anything and make sure you don't have phones. Yeah, just keep it silent. That's all. Okay, and don't take it out during the exam. Yes.
Why don't we have from 7 till 10? Why just 9?
Because the exam is written, it's written to be a shorter thing. So I think usually what ends up happening is almost everybody finishes within 2 hours, and then I'll have maybe 2 or 3 students left.
Are we free to go after 9?
You're free to go as soon as you finish.
Okay.
So if you finish the test in half an hour, take the rest of the night off. That's fine. Okay.
Okay.
So that's that. Yes.
So do we have practice exams?
I don't have practice exams. No, I do have. You have the practice quizzes from before, and I'd say that's a good set of review questions for kind of the calculation-based questions. And as far as the conceptual questions, I recommend kind of reviewing the lecture notes and maybe some of the bold print definitions from the textbook. Okay? Yeah.
Tonight, are we going to be learning new stuff? And if so, how much of that would be on the midterm?
Yes. So the exam will cover chapters 1 through 6. Okay. And today we are covering chapter 6. And so today's stuff will be covered on the midterm exam. Okay. And for chapter 6, I have posted chapter 6 practice problems. Okay. So it's not, you're not going to have a quiz on chapter 6, but I've posted some kind of practice problems that you can see, and you can expect to see similar problems on the midterm exam for chapter 6. Okay.
Not to be technical, but when we have a note sheet, we can type it out, right?
Yes, so your note sheet, the letter size note sheet with writing on one side only, it can be typed. It just has to be created by you. I don't want to see 2-3 different people having the exact same note sheet. Okay, so sometimes it's fine to study together and stuff like that, but when you make your own note sheet, make your own note sheet. Don't just photocopy, print 3 of the same note sheet or something and use it. Do that. Okay. Any other questions? Yes.
So it must be handwriting, or can I type it?
You can type it. Typing is fine. Just it has to be your own. I don't know. Maybe in the vicinity of 40 to maybe more, maybe a little less. 40 to 50, we'll say that. Okay. But as far as time goes, 2 hours is enough time. Okay. Historically, students, I'd say 90% of students have no problem finishing within the allotted time. Okay. All right, then we'll get started on the chapter 6 content. And again, if you, just in case you stepped into the classroom late, I passed out some reference tables, and if you did not get a copy of these 2 reference tables, you can come forward to the front desk and pick them up. All right, so chapter 6 covers what we call probability distributions. Okay, so a distribution, kind of maybe what is a distribution? A distribution is maybe a representation of how the values are spread out, okay? And so, you know, for example, we could make a histogram. So a histogram is a way to display a distribution of numeric variables. And so you could, we might have some histogram that looks like okay, and what do we see in this histogram? We see that values down here are most common, or the lower values. Okay, and then we also have some, you know, high values exist but are less common. Okay, and so this histogram represents how the values in a sample of data are distributed, okay? So this would be, you know, because it's based on data, we can call this an empirical distribution or a data distribution, something like that. Okay. On the other hand, we have probability distributions. Probability distributions are basically theoretic distributions for what we call a random variable. Okay, so it's easier just to say, you know, probability distribution. We can just call this maybe a theoretic or idealized distribution. And so with a probability distribution, you know, we might have something that looks like this, okay? And this shows that the values right here are most common. So values in the middle values are most common. And you know, values out here, less common. So values up high, values down low are also less common. Okay. And again, this is a theoretic distribution, but they are useful because a lot of things in real life follow or can at least be modeled by a theoretic distribution. We can kind of approximate a real life thing with this theoretic thing, okay? Just like we can have a model or an idea of what the ideal coin, how that works, and we say the ideal coin would land heads with a probability exactly 0.5 and tails with probability exactly 0.5. But in reality, you know, maybe that probability is not exactly 0.5. Again, here we have a theoretic or idealized distribution of how the values should be spread out. They should show that, you know, these values in the middle are most common with these exact properties and things like that. And again, it's a theoretic distribution, but it's useful because a lot of things in real life follow these theoretic distributions quite well. Okay, so let's let's take a look. So kind of the most simple example can be thought of as the uniform distribution. And basically, in a uniform distribution, you have two endpoints, and maybe one endpoint is 0, and maybe another endpoint is 1. And this is our theoretic distribution. This basically says that all values between 0 and 1 have equal probability of appearing. And basically all other values have probability 0 of appearing. Okay. Whenever you have a probability distribution, you can kind of shade in the area underneath the distribution, okay? And if you shade that in, the total area shaded is going to be 1, okay? Total area total area encompassed by the probability distribution is always equal to 1. So let's say, and we can use this to kind of answer questions. I could say, here I have this probability distribution, and let's say I ask, what is the probability that I'm going to randomly pick a number I randomly select a number from this distribution. And I will ask, what is the probability that the random value is between 0.2 and 0.6, right? So I can kind of mark these off. All right, so 0.2, 0.4, 0.6, 0.8. And so what I can do is I can shade in the area between 0.2 and 0.6. Okay. And so the question is, how much have I shaded in? What is the area that I have shaded in? Okay. Well, the total area under the rectangle of the entire rectangle is what? This total area is equal to 1, right? So the total area here equals 1. So if this whole thing equals 1, and I've shaded this much, how much have I shaded? I've shaded 0.4. Can we see that? Okay, right? Because we can kind of divide this into like little chunks of 1/5, and here I've kind of shaded in 2/5, right? And so that would be 40%. Okay, and so what is the probability that the random value is between 0.2 and 0.6? Our answer here is that the probability is equal to 0.4. Yes, question?
How do you shade it if you include 0.2 and 0.6 and
Okay.
not just between?
All right, so when we have a continuous distribution, whether it is inclusive of 0.2 and 0.6 or exclusive of 0.2 and 0.6 actually has no impact on the total probability, because the probability of getting any one exact value out to, you know, say a billion decimal points of precision is 0, okay? So, so there's no distinction between 0.2 and 0.6 inclusive or exclusive if it's a continuous distribution. But again, this is an idealized version of how the distribution works, okay? And of course, in reality, you know, we don't have a billion decimals of precision. All right, so this is kind of the most simple one. The kind of the one that we're going to focus the most on in this class, however, is what we call the normal distribution. Okay? Okay, and so the normal distribution looks, you know what, I'm trying really hard. Okay, so it looks kind of like this. It's a hill, all right? It's supposed to be unimodal and, you know, it's supposed to be perfectly symmetric. My art is not perfect, but it's supposed to be perfectly symmetric, okay? This is a probability distribution, okay? Another probability distribution, an idealized version of how data should be distributed. And we're going to start off with what we call the standard normal, okay? So we're going to have the standard normal. And the standard normal distribution has mean, and the symbol for mean is mu. It looks like a U with a little line in front, okay? Has mean mu equal to 0 and has standard deviation. Standard deviation is sigma. It looks kind of like an O with a tail, equal to 1. All right. So do you guys remember what the conceptual definition of the mean was? Okay, not the average, the balancing point, okay? So that's a good thing to remember. The conceptual definition of the mean is the balancing point, and so that means this value right here, which is my balance point, would be equal to 0, right? Because my mean, I just said, my mean is equal to 0. Okay, so that means I have positive values to the right and negative values to the left. Okay, if this is a probability distribution, if I were to shade everything underneath the hill, how much is shaded? What is that total area equal to? What's that? The total area is equal to 1. That's a probability property of all probability distributions, is that the total area, if we shade it, is equal to 1. All right. So just to kind of check your understanding, let's say I draw a line right here and I shade everything to the left. Okay, and I ask, you know, I pick a value from the standard normal. Standard normal distribution. And I'm going to ask, what is the probability that this random value is less than 0? And so the answer to that would be the amount we've shaded, that's less than 0, which is what I've drawn here. And so how much have I shaded? 1/2, right? 0.5. Okay, this area would be equal to 0.5. So the probability that a random value drawn from the standard normal being less than 0 is 0.5. Okay. What we often, because the standard normal is used so often, we often call this the Z distribution. So the standard normal is often called the Z distribution. And this table that you've passed out, this is often called the Z table. And you can see in the top left corner, there's a letter Z. Standard normal is often called the Z. And so this exact same question, we can say, what is the probability that Z is less than 0? Okay. Well, what's the probability that Z is less than 0? We would write 0.5. Is that okay? Conceptually, I hope. All right. Do you guys remember the empirical rule from chapter 3? Do you remember talking about Z-scores?
Yeah.
Okay. All right. And then we talked about the empirical rule. Okay, well, let's all right. Well, maybe someone can tell me what is the definition of a Z-score? Okay, it's a distance, right? It's the distance that, what's that? The distance that our value is from the mean, expressed in standard deviations, right? Distance that a value is from the mean, or I'll just say the distance from the mean expressed in standard deviations. Okay. And then the empirical rule, there were 3 numbers. Do you guys kind of remember those? 68, 95, 99.7. There you go. Okay, great. 68, 95, 99.7. And we said approximately 68% of data is what? Or has Z-scores between, yeah, has Z between -1 and 1. Okay? And we say approximately 95% of data has Z between what? -2 and 2. And approximately 99.7 has Z between -3 and 3. I'm hoping this is familiar. Okay, maybe we forgot the exact numbers, but these are 3 numbers that are good to recall. But it's also important to remember that it is an approximation. An approximation. That's sometimes students think it's exactly 95% and can get us in a little bit of trouble. Okay, so these numbers, 68, 95, 99.7, these are based off of the normal distribution, okay? So I can go out to, I'm going to draw kind of lines here at -1, -2, and -3. And I'm going to go out this way to 1, 2, and 3, okay? And so, you know, if my drawing is perfect, that means that if I shade everything between -1 and 1, the amount I have shaded, this amount is approximately 68%. No? Okay. So if I have about 68% here, how much do I have out here? In total, I would have 32. So how much would be down on this lower side? Yeah, about 16%, right? So down here I would have approximately 16%. And then over here, I would also have approximately 16%. Yeah, whoops, wrong color. Where is it? Okay. And so you can imagine, you know, similar pictures being drawn for, you know, the 95% and stuff like that. So let me how do I do this? This is so terrible. So if I do something similar, but I go out to -2 and +2, then that means the area that I have encompassed within would be close to 95%. This magic. Okay. So this part is approximately 95%, not exactly, but approximately. And how much do I have in each of my tails then? Approximately 2.5%, right? 2.5% in each of these tails. For a total of 5%, but this one is approximately 2.5%, and I have approximately 2.5% in the other one as well. All right, so this is what we have, okay? So I could ask something like, what is, you know, approximately, what is the approximate probability that P is a probability of Z being less than -1? And you would tell me that answer is -1. -1. So you would say this is approximately 16%, right? Everyone's okay with that? All right. What if I said was, huh? Can I repeat that? Yeah. So I'm saying basically I'm going to say, you know, if I draw a line, a vertical line at -1, and I shade everything to the left, how much would I have shaded in? Approximately 16%. Is that okay? All right. And what if I said, what is the probability that Z is less than 2? Okay, again, this is approximation. What's the approximate probability that Z is less than 2? So that's, I'm going to draw a vertical line at 2, and I'm shading everything to the left of 2. How much have I shaded in? About 97.5%, 0.975. Is that okay with everybody? Okay. And so the empirical rule, just by kind of drawing these pictures, the empirical rule can be very helpful for us because, we can kind of get some, some values saying, what's the probability that z is going to be this? But what if I asked you something like, what's the probability that z is less than 1.5? Okay? Or, yeah, what's the probability that z is less than 1.5? Okay. Well, this one's a lot harder to answer because here we would be drawing a line kind of like right here, and we don't know how much that would be, right? So to get answers for all of these other values, we need to use our reference table, okay? Okay, and in fact, the reference table will give us much more precision than saying approximately 16%, approximately 97.5%. So let's take a look. So I'm going to draw a table right here, or not table, I'm going to draw okay, so I'm going to go draw a line right here at 1.5. Okay, and we're going to shade everything to the left. Okay, and we want to know how much have I shaded. All right, so the way our table works is, let me see if I can pull this up here. We're going to, well, you look at each number, okay, and we can see that in the top left corner, flip to the positive side, A3, okay, and we can see in the top left corner we have z is 0.0, and in the column 0.00, that first number is 0.5000, okay? That means if I were to draw a line right here at 0, exactly 0, the amount shaded to the left would be 0.5, okay, and that makes sense, right? Is that okay with everybody? That top corner, 0.0, and then in the column 0.00. So if I shade everything to the left of 0, here I'll just kind of draw this picture. So if I have this and I shade everything to the left of 0, the amount I have shaded would be 0.5, or the table goes out to 4 decimal places and it says it's going to be 0.5000. Okay. And basically, it also says that if I were to go ever so slightly to the right, so instead of 0, but I go out to 0.01, so just a tiny bit to the right, so if I go to 0.01, I would go to the row, my row would be 0.0, but the column that I use will be the 0.01 column, okay? And it says if you go just a tiny bit to the right, the amount you have shaded is not 0.5 anymore, but 0.5040. Okay, so this is just ever so slightly more to 0.5040. Okay, so we can say, the probability that z is less than 0 is equal to 0.5000. And over here we would say the probability that z is less than 0.01 is equal to 0.5040. Okay, all right. So here we want to look up for this purple area. We're going to say, what's the probability that z is less than 1.5? Okay. So we're going to, in our table, we're going to go to the row that says 1.5, and the column, what's our column going to be? The 0, 0 column. Okay, so we're going to go to the 0, 0 column, row 1.5, and what's that number? 0.9332. Okay, so that means this shaded area over here is 0.9332. That's the probability that Z is less than 1.5. Everyone so good? Good so far? Okay, what if I take this side over here and ask how much have I shaded in blue? Okay, how can I answer that? Yeah, exactly. So the table, so this is an important thing. The table always gives the area to the left of Z. Table always gives the area to the left of Z. Okay, and you could even see in the diagrams on the table itself, it always shows that the shaded area is to the left, and it says the cumulative probability for Z is the area under the standard normal curve to the left of Z, okay? So the table always gives the area to the left of Z, and it says so right there on the table. So if we ever draw a picture where we've shaded the area to the right, what we have to do is we have to say, well, we know that the total area is 1, so I can do 1 minus 0.9332. So how much is in blue? We're going to do 1 minus 0.9332. Okay, and when you punch that out on your calculator, you're going to get 0.0668. Is this okay? Do we feel okay with this? So I'm going to give you some practice drills here, okay? So I'm going to ask you questions like, what is the probability that Z is less than negative 1.28? And so for each of these, you should draw a picture. You can put 0 in the middle. And then I'll say, you know, what's the probability that Z is greater than 1.07? Sorry, my pictures are kind of terrible, but they'll work. Okay, so go ahead and take a minute to figure both of these out. You should draw a picture and shade either the area to the left or the area to the right, depending on the question, and come up with a value. Okay, I know some of you guys are still working, but let's take a look. Okay, I was walking around, I saw a lot of good work being done, so that's always a good sign. Okay, so our first one, it says, what's the probability that Z is less than negative 1.28, all right? So I'm going to draw a line at negative 1.28. Now, your line doesn't have to be exactly where it goes, but just, it should be on the negative side of 0, okay? All right, and because it says a less than negative 1.28, I'm going to shade everything to the left of negative 1.28, right? So when we talk about less, we're going to shade to the left of something here, okay? So I'm going to my table, and I'm going to look up the row. What's the row I'm going to go to? Negative 1.2, and I'm going to the column 0.08. Okay, and the number I find there is 0.1003. Okay, so the table gives me the area to the left. Is it the area to the left that I want? Yes. Okay, so this is the value I want, and so that number is 0.1003. Okay, so this is the area to the left of z equal to negative 1.28 is equal to 0.1003. All right, is that okay? All right, let's take a look at the other one. So over here it has, what's the probability that z is greater than 1.07? So I'm going to draw a line over here at 1.07 because 1.07 is positive. I'm now going to shade this area over here, okay, because it says greater than, right? So over here I want the area greater than, so this means I'm going to take the area to the right. Okay, so I want this. So I'm going to the table and I'm going to look up, what's the row that I go to? 1.0. I go to the row 1.0 and the column 0.07, right? So we look at what that is, and I go to 1.07 and I find the number is 0.8577. Is that my answer? No, right? 0.8577 is the area to the left. The table always gives you the area to the left. So this is the area to the left. What we want is the area to the right. So the area to the right is going to be 1 minus this chunk. So 1 minus 0.8577. And that gives me 0.1423. Okay? And so this answer is 0.1423, or my answer right here, 0.1423. Is that feeling okay? All right. Okay, so let's. This is nice and all using the z table, but this is most useful when we apply it to kind of like a situation with maybe like a real life situation. Okay. So we can say something like cholesterol levels in people. Follow an approximately normal distribution. Okay. So we'll just say follow a normal distribution. Okay. Except the mean cholesterol level is going to be something maybe like 190. Okay. You know what, let's say 200, okay? So we'll say the mean cholesterol level okay, and the standard deviation is 30, okay? So these are just kind of rough numbers, but we're gonna just pick some nice even numbers for us to work with here, okay? So the mean cholesterol level is 200, the standard deviation is 30, okay? So if we draw a picture, this is what we have, okay? All right, just a quick check. I'm not even going to bother drawing this, but what is the number that goes right here in the middle? Okay, so if we were talking about z-scores, we would put 0, okay? But now we're talking about cholesterol levels. So what is the number that's going to go in the middle for the cholesterol? 200, because it says the mean cholesterol level is 200, okay? And so you can kind of think on one scale I've got cholesterol levels, okay? And we can think of, you know, if I convert the cholesterol level to a z-score, you know, if we convert this to a z-score, what does this 200 convert to? It converts to a z-score of 0. Okay? So we could say, you know, if I said, what's the probability that z would be less than 0? You would tell me that probability is 0.5, right? Okay. I could ask, what's the probability that the cholesterol would be less than 200? This is pretty much asking the exact same thing. We've just converted cholesterol to z, and when we convert cholesterol to z, 200 gets converted to 0. And so the answer here would also be 0.5. Okay. How do we convert a measurement into a z-score?
X minus mu.
So yeah, so our z is going to be x minus mu, but we don't leave it there. What do? Yeah, we take that difference and we divide by the standard deviation. Okay. So let's say someone has a cholesterol level of 150. Okay. So we'll say, I can ask the question, what is the probability that a random person's cholesterol is over 150? Here, actually, I'm gonna just slide this up over here. So this is going to be my question. What's the probability that a random person's cholesterol is over 150? Okay. So this is essentially asking, what's the probability that cholesterol is over 150? Is that okay? So on my picture, I'm going to draw a line at 150. 150 is lower than 200, so it's going to go down here. I'm going to draw a line, and I'm going to shade in everything to the right over there. Okay, so we're going to shade in over here, and we want to know how much have I shaded in. Okay, so right now I've got cholesterol. I can't look up cholesterol on this table. This only has z-scores, and the numbers I can look up are really between like -3 and +3. So what I have to do is I've got to convert my cholesterol into a z-score. Okay, so we're going to convert the number 150, which is a cholesterol number, convert that into a z-score. Okay, so what we're going to do is, number one, convert 150 to a z-score. Okay, so what is 150 when we turn it into a z-score? It's going to be 150 minus 200, and then I would divide that difference by 30. Okay, so what is my z-score going to be? -1. I'm going to just round off to two decimal places. Is that okay? -1.67. So convert 150 to a z-score, and then I'll say round to 2 places. Okay, so when you turn something to a z-score, you round to 2 places. So effectively, instead of 200, when I convert this into a z-score, I'm going to have -1.67 here. Okay. So now I'm going to ask, what's the probability that cholesterol is over 150? Basically, I can just say, what's the probability that z is over -1.67? Okay. So I want the area to the right of -1.67. So what do? I look up. I'm going to go to the row -1.6 and the column 0.07. And that number I get is 0.0475. Okay? And that's the area to the left. Is that okay with everybody? No? I want the area to the right. Okay? So to get the shaded area, what do? I'm going to do 1 minus 0.0475, and I get this area equal to, I don't know, something else, 0.9525. 1 minus 0.0475, 0.9525. Okay, and so that's going to be my answer. The probability that the cholesterol is over 150, 0.9525. So we convert the cholesterol number into a Z-score, and then we look up the Z-score in the table, and now we can get our answer. Is that good? Let's. I'm going to give you guys an example to work through, and then we'll take a short break. All right. So let's say the height of, we'll say, men in the U.S. is approximately normal. Normally distributed, I should guess. All right, and we'll say the mean is equal to 70 inches, and the standard deviation we'll say is 2.9 inches. Okay, so I will ask what percentage or what proportion of men in the US are shorter than 6 feet tall. So we'll say 72 inches. Okay, so I would advise drawing a little picture. You gotta figure out what number to put there, where to draw your line, and figure this out. So effectively we're asking, what's the probability that height will be lower than 72? Okay, so I'll give you guys a few minutes to figure that out, and then we'll go over the answer. I'm gonna pause the video here. All right, let's go over the answers. Walking around, looks like a lot of you guys are doing great, so that's very encouraging to see. So in our picture, we're going to put 70, the mean, right in the middle, and we're going to draw a line at 72, and we want to know what percentage is shorter than that. Okay, so we're going to shade everything to the left here. All right, so we've got to convert 72 into a Z-score. Okay, so 72, we do 72 minus the mean of 70, divide by our standard deviation of 2.9. I'm getting something like 0.6897. Okay, now when you find a Z-score, round to 2 decimal places. Round to 2 places, and that's because the table only gives us 2 decimals of precision. Okay, so we're going to use Z equal to 0.69. Okay, we look up 0.69 in the table, and the area to the left, so from the table, we see the area to the left of Z equal to 0.69 is 0.7549. Okay, and is that the answer I want? Yes. Okay, because our picture shows us that we want the area to the left So we want the area to the left, and we're going to say our answer is 0.7549. So what proportion of men in the US are shorter than 72 inches? Approximately, according to these numbers, about 75%. 75.7549. This is our answer here. Good with everybody? Any questions? Okay, why don't we take a break here? We'll say 10 minutes, and then we'll come back and we'll finish up normal distribution stuff, and then talk about the binomial distribution.